So.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is the ebook series. And I am super happy to have ebook author Nicole Lloyd-Ronning with us today. Hey, Nicole.
Hi, Frank. Hi, everyone. Thanks for having me.
It is lovely on this December 21st of 2022 as we record this. And Nicole, where are you located at?
I am in Los Alamos, New Mexico.
Very nice. So we must have snow there, 6,000 feet or so.
We wish we had snow. We have a sprinkling on our mountains in the Jemez, but not enough. Not our ski hill is not open yet, but we're all crossing our fingers as hard as we can. Hopefully soon. It's very cold, but no snow.
I bet. Well, yeah, 6,000 feet. You're still cold.
Yes.
We have no snow in Phoenix.
Oh, surprise.
But if you go up to Flagstaff, you'll probably get plenty of snow. So
yeah.
It's going super well. Very cool. Looks like you got a little festivity going there on your lights to your left.
Getting ready for Christmas. 2/3 of the kids are home. One is stuck in Vancouver. They're getting a lot of snow there, and his flight got delayed by days and days, so he might not make it home till the very last minute, but we're hopeful.
Well, cross fingers he gets in okay.
Yeah.
Nice family reunion.
Exactly. It'll be good.
Very cool. And Nicole, what do you like to do for research?
So everything, but mostly gamma ray bursts. So the spectacular deaths of very massive stars, creating a black hole disk system and launching a relativistic jet. And I love studying every single part of that, the progenitor system, the black hole disk physics, how the jet is launched, the plasma physics in the jet, and then the jet's interaction with the external medium and what that means. I really like connecting to that to what we see. What does that mean for us? It's fun to make toy models, but it's even more fun to say, what are we going to see when this brightest explosion in the universe goes off? So that's what keeps me busy.
Very cool. And I assume this will be one of the chapters we're going to cover somewhat soon.
I'm very biased in what I love to research.
They're completely solved yet. So
yes.
So let me ask, what gave you the idea to do an ebook on this topic?
It's a good question. I had thought about writing an astro book for years that was accessible to the general public. And in fact, cool. I had taken a long career break. I left the field for 10 years. And when I was first thinking about coming back, I had tried to write children's books on really somewhat esoteric topics like dark matter and dark energy, but for kindergartners. And I didn't really have success. I tried and I had a little bit of interest from one publisher, but nothing panned out. And so, I kind of got back into work at the laboratory and at UNM at the University of New Mexico, Los Alamos, where I teach physics and astronomy. Cool. And at UNM, I got involved with their community education program. So this is classes open to the whole community. Anyone can join. They're like $25 for a semester. And I wanted to teach a class that was called Modern Topics in Astrophysics, and that brought hot research, the latest hot topics in astrophysics research to the public. And everybody was welcome in this class. And indeed, we had some high schoolers, we had retirees, we had folks who were sociologists, we had a woman with an 8th grade education, we had PhDs in physics. So we had this huge spectrum of learners in the class, but I wanted to communicate astro to them. They were all interested. That was the common theme among everybody in the class. So that went on for 5, it's actually still going on now over Zoom. It went on for like 5 years live. And then in the pandemic, we moved it online, and that's how we're doing it now, because a lot of people moved. But anyway, from that came this idea, why don't I try to write those things down and see if anyone cares, if anyone's interested. And the IOP is sort of the perfect, they had it very timely at the beginning of the pandemic. Was it the beginning? No, it was 2021. It was sort of in the middle. I was losing my mind. Yeah. And they had put out a proposal to the American Astronomical Society, or a solicitation for proposals for books. And I thought, well, I've had this idea and let's try. So I wrote a proposal, and they don't typically, I think, do general public kind of science books. It's a little more focused for researchers and a little more technical.
Right.
I think, but they were open to it, thankfully, and the reviewers of the proposal were positive about it. So that's how it all got started. This was, back in April of 2021, I think it was.
So that's when you actually started writing, was March or April 2021?
Yeah, I think I began writing in April of 2021. That's right.
It's about a year and a half.
That's right.
Start to finish.
That's right.
Do you have a hard copy of your finished product?
I do. Thank you for asking. You can get, there's a bit of a glare. You can get a hard copy if you want, but it's also, of course, an ebook publisher. So however you prefer.
Very cool. Very good. Well, let's go ahead and dig in, and let's take a look at some of these mysteries of astrophysics.
Awesome. And I should mention that I originally called it Greatest Mysteries in Astrophysics, and one of the reviewers somewhat said, well, that's an opinion. And I was like, okay, that's fair.
So, Great Mysteries in Astrophysics, a guide to what we don't know. And Nicole, take us away.
All right. So the main thing I wanted to do was convey, not just sort of spit out, here's what we know about our universe, which is a lot and impressive, but really try to highlight the places where we lack understanding. And I think a big motivation for me also is, thinking that a lot of us have been working on a lot of these problems for a lot of years with not a lot of progress. And maybe we're not bringing enough people into the conversation. Maybe we could be more inclusive about the way we're approaching some of these things. So a big motivation for me was, and trying to make this accessible to everybody too, is to bring more people into thinking about these problems. So maybe we can have some new ideas and new solutions. We can go scroll down a little, I guess, and
look at the content. There's a little bit about the eBooks and some of the corridors we publish in. There's the editorial board. Steve Qualler heads up that editorial board, and illustrious people on the editorial board. And Great Mysteries, copyright, and contents. Let's walk the table of contents.
All right. So one thing the IOP had asked is if I would begin, since it was a general level book, if I would begin with a little bit about how scientific problems are solved. Mm-hmm. And I know, like, we all learn sort of a very standard recipe, at least in schools in the US, we learn some sort of standard recipe when we go to science fairs, which in my experience is not how it actually works. So there's nobody saying a hypothesis and then you do an experiment and then you test. It's not like that, like your science fairs in elementary school. So I tried to highlight some different problems, some that were a little more experimental, some that were more theoretical, some where the experiment drove the science, and some where the theory drove the experiment. I wanted to start, this was right in the middle of the pandemic, so I wanted to highlight the amazing work that was done to develop the COVID-19 vaccine. I think, we all benefited so much from that. A little bit about the Higgs boson, because there was the theory first, and then many, many years later, we discovered that particle. And that is amazing to me, that we can ideate this and then there's something reality that comes from that. And then there was a really interesting example to me about the handedness of dolphins. This which sounds ridiculous, I realize, but there, in the literature for a long time, there had been a suggestion that dolphins have a preference to spin to the right. And this turned out, when some thoughtful researchers really looked at what was going on, this turned out to be a a bias of the experimenters, that no matter which way they were spinning, they were calling it to the right. So I brought up this example to really try to emphasize we're humans and we're biased, and we need to never forget that. We do not separate our humanness from the science ever, no matter how much we want to. It matters, and it plays a role, and it can lead to us down the wrong path sometimes. So we have to be careful and acknowledge it. So that was, the start. But then I wanted to move on how astrophysical mysteries are a little different in this from these initial examples, simply because we cannot, for the most part, except for maybe to the moon and some nearby planets, we can't go to our experiments. So we're sort of, it's like a little bit more like forensics. We sit back and we receive information from the universe and we try to make sense of it. So I tried to give some examples of what I think are some of the coolest discoveries in astrophysics, and how those played out, and they again span a range of theory and observational, I would say. So I discussed some of those problems, and finally end this chapter with a little bit on how we've gotten things wrong, and how science kind of it isn't always perfect, and the important thing is that we always acknowledge it and evaluate it and test our ideas. So and I just discuss a few examples of that in the mysteries throughout history.
Cool, nice.
So yeah, so then the next part, before we start talking about the mysteries, I just wanted to go over the ways that we, quote, see the universe. I had always thought just you look up and you receive light from the universe. And then even when you talk about light, in my mind growing up, that was just what my eyes could see, but light means a lot more than that. So I first talk about the entire electromagnetic spectrum, all the wavelengths of light that we cannot see, and that information that brings to us. But then I also discuss how objects in the universe send particles, and massive particles. So not like something different than light, like cosmic rays and neutrinos. I talk about how the universe also sends us gravitational waves, so ripples in space-time. So a little bit about what those are and the information that brings. So this is sort of how I break down the main types of information that we collect from the universe, and then how it tells us something about the objects that make these different messages. I'll say. Sorry, go ahead.
Multi-messengers, yep.
Multi-messenger, exactly. It's a hot word right now. And then finally, just a little bit about remembering that when that light, or any of these messages, light and particles and gravitational waves, take time to travel from the object that created them to us. And so when we're looking farther back or farther out in the universe, we're looking farther back in time. So just emphasizing that point of how we can get a historical view of the universe in some sense.
Right. It's like an archaeological dig.
Archaeological dig, exactly. So then I move on to the mysteries. And I start by, taking an inventory of the universe. And I talk about all the objects that we know of in our universe that are made of matter that we more or less understand, baryonic matter, and so atoms on our periodic table that make stars, and I kind of give a little bit of the types. I give a rundown of the types of objects in the universe. It's not exhaustive, but I try to talk about different types of stars and their evolution, or different masses, and then what a galaxy is, what a cluster is, and things like that, just to give some context. But then I talk about some of the mysteries associated even with the stuff we think we understand, like why do we live in a universe with more matter than antimatter? Why is there not enough lithium, or we don't observe the lithium we expect from our understanding of the early universe, things like that.
Yep.
But I get excited to move on to some of the bigger mysteries in our universe's inventory, which to me is dark matter and dark energy. So I move on to talking about evidence for dark matter, so mass that we know is there from its gravitational influence on things around it, but it doesn't emit any light. We can't detect it. We haven't caught it yet in terms of a particle. So just, what is that? And mostly I go through the evidence that it exists, but not a little bit about the options of what it could be, but I think that's a playground right now of what is it? And so that's, to me, one of the great mysteries. Yeah, and then even bigger, even more of a playground is dark energy, which makes up 70% of the energy in our universe. And I again talk about the evidence for this energy of our universe. It's, we infer it from our observations, and there's been amazing work. And I really try to emphasize the way the observers have done their work, and done a tabulation of an inventory of the energy of our universe. That, there's evidence that there is something out there, but we don't know what it is. We do know it's causing our universe not only to expand, but to accelerate in its expansion. So I discuss a little bit about that. So I end this chapter with, we don't really know what 95% of the universe is made of, but we know it's there. We just don't know what it is, and that's exciting. That's exciting
for it.
Yes. And I'll mention at the end of every chapter, and this was a suggestion I really appreciated from the IOP. They asked to offer further reading and things like that. So every chapter has a list of references where you can get more info from the very technical journal articles to the more popular science books about these topics.
Good, nice range there.
Hopefully, yeah. So since, we ended the previous chapter on dark energy, we move on to the expansion of our universe. So looking back at sort of, how it all began, and how is our universe behaving now. And what describes the expansion of our universe is something called the Hubble parameter, the Hubble constant. And this is a description of how fast our universe is expanding and how it is expanding. And this has been since the discovery of our universe's expansion early in the early 1900s, how our universe is expanding has been a debate, through the years. And when I was, an undergrad, I remember it, being a fight that the value was 50 kilometers per second per parsec versus 100. It was the 50 versus 100 camp, and it was a big disparity. And then in graduate school, everything converged around 72, and everybody was happy. And we're like, we've solved it. And then the measurements got better, and things have diverged again, which is so exciting. There's something weird going on where the measurements in our early universe don't really match the measurements in our more recent universe. Right. And so I try to discuss that. But
at least it's not a factor of 2 anymore. At least it's not 50 or 100.
Exactly. That's true.
But that's still tension. Yes. There's
still tension. And I do talk about how there's room that there's some issues with the way that we understand how we're observing and correcting for some dust and things like that in the foreground, or systematic errors. So that, it may not be, some kind of new physics, but it might be. So it's just an offering of the state of the Hubble constant debate at the moment. Yeah. So that's that chapter. And then from there, and within that, I hope I give a kind of a history of the expansion of the universe, so folks get a sense of our universes growing up from what we call the beginning to now. But then I start to talk about how did the things that we see with our eyes when we look up in the sky, stars and galaxies, how did that all begin? How did the first stars form and the first galaxies form? And, we understand stars pretty well, and we have lots of great observations of lots of great galaxies, but it's fascinating to me what we don't still understand. And so I try to to explain a little bit about some of the mysteries about and things that we still need to learn about what was going on when that early universe gas began to clump and form stars and clump further and form galaxies, or maybe there were giant clumps and everything formed at once, or how that all happened. So this goes through a little bit of those mysteries. And the reason why, you might ask, why does that matter? And actually, I hope at every point you ask, why does this matter? And I hope you get a sense of why it matters as you read. But to me, this plays out in the evolution of our universe from the early times till now. So I think it's a really important problem. And it means a lot for how we understand what's in our universe and how it behaves.
Probably written a little bit before some of the JWST results came out. And I think some of the JWST stuff will start addressing aspects of first stars, first galaxies.
Exactly. I did. This was submitted right about a few weeks after their initial image in July. And then all that exciting stuff about the really high redshift galaxies came out. I think I was able to put in a few sentences about that in there. And I even got a couple images in there as figures. Cool. But that is definitely, and I do have a paragraph on what JWST will bring to this field, actually, and it's very exciting. I'm excited for that.
Very modern, okay. Very modern. Very good.
Yeah, at the moment. We'll see.
Now you want to take two stars and you want to put them together. Oh no.
I do. And so this is probably, also from my cutting my teeth on astrophysics research. I tend to think of things in isolation. And as I, look into more and more of these issues, I realize, just like with humans, interactions are everything. We, the way, going back to these issues of first stars and first galaxies, and the universe was denser, it was crowded, things were colliding and interacting, and this matters in a big way. So this chapter I tried to devote to why interactions matter between stars and between galaxies and everything in our universe. So it's all dynamic and influencing one another. And so I tried to emphasize that point, but then go into some of the more specific problems that we don't quite understand, like how are things, these binaries or these multiple systems, how did they form? Were they born that way, or did they capture each other later? And how did that influence the members of the system? Does the star look the way it does because it's in that binary system, or because that's how it is by itself? And similarly with galaxies, we've had this problem for years with simulations, that we were way overproducing dwarf galaxies in our cosmological simulations. Yep. And then we started to observe them, and now we're not doing enough. And how does this all fit in the context of some of the stuff in the previous chapters of our view of our cosmology, of our cosmological model, of the inventory that we have in the universe, of the amount of energy we have in these different components? How do we make sense of all of this? And we still have a lot to learn there, a lot of problems in some sense of what, how to understand the formation of these objects and how they matter for us.
Mm-hmm. Very cool.
So that is this chapter, and then I go a little zoomed in on things. Then I pick. There has been my bias up until now, but really here's my research bias. I am so fascinated by stars in general, but massive stars particularly fascinate me because of what they do when they're done burning out their fuel. And so I discuss how massive stars die, and supernova, types of supernova, and the things that we don't understand about that process when a star sort of a massive star explodes on its death. And then you've highlighted gamma ray bursts. I do go into a chapter on gamma ray bursts. I did my best not to write another whole book on this because I love them, and there's so many problems at every level. I mean, they span the whole. They're called gamma ray bursts, but they emit from the radio to the TeV gamma rays. They are They span the whole electromagnetic spectrum. They're multi-messenger objects. They span physics in all its different parameter spaces.
Yep.
So to me, they're just so fun to work on. And there's so many things that we still have to learn about all these processes which are connected to our fundamental understanding of physics. I think that's why I like them so much, is that they provide a laboratory for us to probe very extreme physics that we can't create on Earth. And I we have lots to learn there. It's exciting to fill in some of the gaps in our knowledge of some fundamental physics through these very extreme objects. So I talk a little bit about what they are and how they work in, with the caveat of this is what we think, but there's lots of them there. Exactly.
Cool.
And then I move on to talking about how we understand matter at very extreme densities. And the best laboratory, in my opinion, for that are neutron stars. So the densest stars in the universe and that are made in these supernovae explosions. And there's so many different interesting topics associated with these neutron stars. So I do talk a little bit about the to physics of super dense matter and what we don't understand there. But also just the range of objects, observational phenomena that neutron stars provide us, from what are called ordinary pulsars, where we see their light beams sweeping in and out, and even those are sort of the there's thousands of them, and there's sort of I don't want to say boring of the neutron star phenomena, but even the ones that we've studied the most, we still don't understand everything about those. And that's awesome to me, that we still have things to learn there. Then I go into some more extreme things like magnetars, neutron stars with very high magnetic fields, fast radio bursts, which has been such a fun field to follow over the last 10 to 15 years, and watching CHIME and other detectors come online and observe so many of these and start to associate them with a magnetar or in a globular cluster, or things like that, have in some ways enlightened us and in some ways brought up more questions. So I love that field and talk about that a bit. And finally, I end with neutron star mergers and heavy element production, and just a little bit about how we get the periodic table in our universe. This is a really important question for our existence, really, and we have lots of questions there about where the elements above iron or so are produced, and so I talk a little bit about that problem and how neutron star mergers have shed some light on that and shown us some evidence for that, but that there are still questions there that we need to answer. Yeah, and then I move on to the next level of extreme matter. Yeah.
Level of compactness. There we go.
Yeah. Yes. So black holes, this is the last sort of content chapter I have. This is that's okay. Again, a huge bias in what I think is interesting. I think about black holes on a daily basis, many times a day, and I love them. And so I try to walk through all the things that we don't understand about black holes beyond, I get a lot of questions when I give public talks. What happens inside a black hole? What's going on in the black hole? And I do mention that, like, we don't know how to write down those equations yet, and there's some really interesting problems associated with the physics there. But I present this chapter in a more astrophysical context. So I do talk about the absolutely solid evidence, including direct imaging, that we have for black holes, because some folks, I think, still wonder, do they really exist, or is it just a flight of fancy for theorists? So I talk about all our evidence and the many ways they play out. And then I try to step through problems associated with different masses of black holes. So the stellar mass black holes, then there's sort of intermediate mass black holes in the thousands solar mass range. And then the supermassive black holes that are, you know, 1,000,000 to tens of billions of solar masses, and in particular, how they got so big so early in the universe, going back a little bit to some of the James Webb early, you know,
Right.
seeing things forming in the early universe. We're seeing these supermassive black holes very early in the universe, and how did that happen? How did they get there? A little about the black hole disk phenomenon. So when they have a disk around them, all the interesting physics going on there. And finally, just a very short section on what are called primordial black holes. So the black holes formed in the early universe, that, you know, could be very tiny. They don't fall into any of the classes above. They could be, you know, extremely low mass, you know, grams even, or, you know, whatever. And a little bit about their evaporation, a little about Hawking radiation and potential signatures there, and how they might play a role.
Nice.
And then finally, I try to end the book on a somewhat, you know, hopeful note about, so we have all these problems. I didn't, you know, obviously again, I will say I gave my biases toward what I think are interesting problems. My colleagues will say, hey, you left out, you know, 4 books of interesting problems.
It's all a problem.
Exactly. There's so much. There's so many things we don't understand. And at the same time, you know, I'm blown away by how much we do understand. So I try to balance that we know a lot, and we have tools to continue to learn. We have a lot to learn. I do talk a little bit about a couple of other problems that are kind of cross-disciplinary, like quantum gravity, a little bit about the origin of life, some other, like I briefly mentioned some other problems that I don't go into in detail, but all kind of connected in some sense to the theme of mysteries in our universe, and connected to the physics that was discussed previously in the book. And then I tried to kind of look forward on how we might be responsible about going about solving some of these problems, with our instrumentation and where and how we build our telescopes, a space exploration and being responsible about that, and collaborative. And I think that's how I really end the book, is thinking that we need to be a little more collaborative. We have historically not been, and lots of folks have been excluded from being able to try to solve some of these problems, and maybe we can do better there and make some real progress.
Yeah.
And that's that.
Very cool. Very nice. Nicole, thank you so much for walking us through great mysteries in astrophysics.
Thank you.
And I liked how you touched on the end there about the future stuff. And so let me ask the question, do you anticipate, and hopefully it doesn't take a pandemic, do you anticipate volume 2 of Great Mysteries, like maybe, I don't know, 10 years or so? Some of them will be perhaps solved a little more than others, and there'll be new mysteries on the horizon. And so
I hope so. Yeah.
For Great Mysteries 2.
I hope so. Yeah, there's sort of 2 axes there to me. One is that what I think you're saying, in that, you know, updating this in the sense of what have we learned. We will, you know, as I was writing this, I was like, these fields are changing quickly. Our technology is improving, our observations are improving. We will learn, and this will be dated, who knows when, but I would love to update it with fresh information and modified mysteries, in the sense, or maybe some of them are solved. So there's that, and that, yes, absolutely. And I, you know, everything I wrote about, I follow those fields as best I can to keep fresh on that. But then also, you know, like I said before, these are my biases about what I think are interesting problems, but my colleagues feel otherwise, and I appreciate that so much. And as I learn more about their fields that I don't know anything about, maybe there's room to write a different type of mysteries book.
There you go. There you go.
So, yeah.
Gather a few of your co-authors who think other mysteries are
Exactly.
good. So very cool.
Exactly.
Very nice. Nicole, thank you so much for walking us through your very lovely new ebook.
Thank you, Frank. I really appreciate it. Thanks for the opportunity.
Yep. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.